So today let's take a look at a super cheap clock mechanism from China. It's a quartz clock mechanism or movement which looks about like this, and you can use it to repair some clocks or to make your own DIY clock. It's basically this mechanism and some hands which look about like this after the shipping, and this is the second hand, also really nice because it was wrapped in just this bubble foil and in a plastic bag, but for 79 cents including shipping you just can't complain. The listing says some keywords like DIY clock, wall, quartz, movement, spindle, mechanism, tool part, hands, repair. You can use it to repair various wall clocks or to make your own DIY clock. If you want to make your own dial or a box for a clock, this mechanism is definitely useful for you. It's also useful to repair clocks if the mechanism is broken in it, but don't use it to repair antique clocks. Never use it to repair a clock like this because you're gonna completely ruin it. This antique clock is much more valuable with the original mechanism even if it's not working. Any mechanical clock or any clock which may become valuable in the future shouldn't be repaired using this Chinese rubbish. And before opening it, let's try to put it into operation. It runs on one AA battery, and here's the mechanism, the hands, the second hand, minute hand, hour hand, and something for mounting, a washer, and this nut which goes onto this screw like this. So let's try to install the hands after straightening them because they are bent. The hour hand goes first. You just press it onto it. The minute hand looks like this. It's trying to imitate the vintage hands like in antique clocks, but it's just a cheap imitation. Very cheapish, very thin. This is just absolutely flimsy. And the second hand. And this one has a counterweight on it because it's moving fast, and without this counterweight it may have problems traveling upwards like this. So let's install it. Does it fit? Kind of. Okay, that's it. Now let's try to run it. The battery goes in like this, or maybe not. Yeah, it does. Is it running? Yeah, it seems to. So it's running. Maybe it will get stuck now because it's completely bent. Yes, it got stuck. Let's bend it. It kind of runs. You have to keep it all straight because otherwise it will collide. You have to kind of put all of them into one direction and straighten it like this, so there is no collision. Sometimes it's a bit tricky. Now it should be okay. It's running. So it's running, and when you try to move the second hand, you can hear the motor spinning very fast. When you move the minute hand, the hour hand is moving through the gears. But when you move this one, the hour hand, the minute one doesn't move. It's possible to set it moving the minute hand like this, but it's better to set it using this wheel here. You can set it like this without actually touching the hands. it's probably safer. You don't touch the hands, you don't bend them, you don't damage the wheels in it, the gears, and also some clocks have a glass over it, so you can't even touch the hands. And of course you can install it without the second hand if you want. You can leave it like this. And of course when installing the hands you have to put it into sync. So when the minute hand is showing 12 like this, the hour hand should show a whole hour. For example 3. It should never be in between like this. This is wrong. So here's the mechanism, and the second hand is on a thin metal shaft which is inside of another shaft which is hollow, and this one is for minute hand. And the hour hand is on the biggest shaft, and there are gears in between, and from the second hand to the minute hand it's geared 1 to 60, and from the minute hand to the hour one it's geared 1 to 12. From this side you can see just the shafts and the screw for mounting, and from this side it has a battery and it's slightly transparent. You can see some electromagnet in it, some gears, and this setting wheel, and the space for the battery. It says quartz, and it has no jewels or 0 jewels, and it's unadjusted. Quartz means it has a crystal to control the running speed. 0 jewels means it has no jewels in the bearings. And unadjusted means it has no adjustment. You can't adjust the running speed of it, like in the old clocks. Because the old mechanical clocks used to have jewels, some kind of sapphires or ruby crystals to make bearings for the shafts of the wheels. But maybe it's even nowadays, especially in the expensive watches. Now let's try to measure the current it draws. It's about 1.5 milliamps. That's quite a lot for a clock. It's not gonna last very long. It draws 1.5 milliamps, and a typical AA alkaline battery has about 2000 milliamp hour capacity. So let's do some calculations, and this is my new calculator. Not actually new, but new to me. It's probably from 70s or 80s. It has a vacuum fluorescent display instead of LCD display. It works quite well, it has nice clicking buttons, and here's my cat coming to help me. So let's do the calculation. 2000 milliamp hours divided by 1.5 milliamps. And that's about 1300 hours divided by 24, and that's in days. About 55 days divided by about 30. Now it's in months. So it's gonna last less than 2 months. That's not very long for a clock which is continuously running. So the power consumption is quite disappointing. And it seems like there are 2 types of those quartz mechanisms. One has a motor which is continuously running, and the other type has a motor which runs in pulses. Can you see the difference? This one is just moving continuously, smoothly. And this one is running in pulses. This one is moving once every second. This one clicks, clicks, clicks. This one runs continuously. And I guess this one is more power efficient, but it's not easy to measure the current because, as you can see, it runs in pulses. But this one is already running for about 2 or 3 years with the same battery. It's also a AA battery, and let's measure it. How much did it discharge? 1.34. So it's still gonna run for another 2 or 3 years. That's nice. This one is gonna run for 2 months. That's quite crappy. But now let's finally take a look in it. It has no screws, and the cover probably just clicks in. Here and here. So let's remove the cover, and now it's probably gonna fall apart. Let's try to carefully open it. It also clicks here. Now it should open. And that's it. Here you can see the setting wheel and the other wheels, which are now loose because this one works as the bearings. Here's the stepper motor in it with a coil. Here you can see the crystal and the core of the electromagnet or motor or whatever you call it. Here's the rotor, and it's geared down using several gears until it goes here, and then it continues here into the second hand, into the minute hand and hour hand. Can I run it when it's open? Kind of. It turns. That's probably not very happy without bearings. So here you can see the gears. This is the rotor, and this is 1, 2, 3. Another 3 gears before it reaches this one, which is probably the second hand. This is the shaft of it. So let's remove those. And this one. Here is the rotor, which is still spinning. Can I take it out? Yes. And it has a magnet in it. So it looks like a synchronous motor. It has to be a synchronous motor for accuracy because an asynchronous motor has a slippage which changes with the load, so it wouldn't be accurate. So this one shows seconds, and it goes into another wheel. And this one goes into one more wheel here. And this one is probably minutes. And there is another wheel here and another wheel here. And this one is hours. So it goes so there are 2 gears from seconds to minutes and another 2 gears from minutes to hours. So it slows down, but it keeps the same direction of movement. So let's open it further, removing this one, and can I take this one out? Yes. Now it probably completely falls apart. Here you can see those 2 gears with the hollow shafts for minutes and hours. And this screw in it. And here is the mechanism or the rest of it, with the shaft for the seconds. So here is the wheel with the shaft for the seconds, and it seems to have some kind of brake on it. So let's take it out. And what remains is this coil with the core and this tiny circuit board with this crystal, probably 32.768 kHz, and a chip under a black blob, and those contacts for the battery. And here you can see the ends of the coil soldered to it. And those contacts of the battery are going here to those contacts, which go from the contacts of the battery, of course. From here it goes here, and from here it goes here. And that's it. So it has almost no components, just the battery, the chip, the crystal and the coil, and that's it. What is the frequency it spins at? Let's try to make a mark on it. It's quite fast. Maybe 10 times per second or 5 times per second. Can you hear it? But most likely it is 8 Hz because you can get this frequency from this one using a binary division. You can divide it by 4096, which is 2 to the power of 12. You basically divide it by 2 12 times. So this is the frequency of the crystal divided by 2 for the first time, second, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you get 8 Hz. So that's how the accurate frequency is generated for the motor. Can I measure it? The contacts of the motor are from the other side. So let's drill some holes in it to measure it. Yes, it is 8 Hz. Let's also connect it to a scope. So here it's on a scope, but because it's quite a low frequency, it's better to take a picture of it. When the frequency is low, the scan rate of the scope is also low, so it's better to take a picture of it with a long shutter. Now let's try to print it. So here you can see the pictures of the scope. The first one is just with a single channel, and this one is connected to the terminals of the coil, and the sensitivity is 0.5 volts per division, and the time base is 20 milliseconds per division. And it looks like this. It's kind of a square wave with a dead time. And it is about 1, 2, 3, 4, 5, 6 divisions. So the period of the signal is about 120 milliseconds. And the voltage is about 3 divisions times 0.5 volts. So the voltage is about 1.5 volts here, and it's about minus 1.5 volts here. So the voltage is 0 volts, 1.5 volts, 0 volts, and then minus 1.5 volts. And then it repeats. And the second picture is with 2 channels. Each channel is connected to one terminal of the coil, and the ground of the scope is connected with the negative of the battery, like here. Now the sensitivity is 1 volt per division, and the time base is the same. It's 20 milliseconds per division. And it looks like this, with 2 channels. Now the signals are about 1.5 divisions, and because it's now 1 volt per division, it's 1.5 volts. And here it's 0 volts. So each channel is 0 volts for most of the time, and then it makes 1.5 volt impulse. And those 2 channels are alternating. The chip probably contains a bridge with 4 transistors driving the coil like this. So it's back together with a blinking LED added to it, using a voltage doubler like this. So this is Diagon Wild, and see you in my next videos, and thanks to all of my patrons on Patreon. I really appreciate your support. Can I turn it into a turbo clock using a higher frequency from a 555 oscillator?